Hello everyone. I think we can start now. And yeah, I would like to thank you for all joining our webinar today with our demonstration site 6 in Geneva and with the title Intelligent, Electrified and Sustainable Mobility at the Heart of European Innovation. First, I would like to show you the agenda. First, we make like a small introduction. Then I have a brief presentation of the speakers. And then we have an overview about the ENFLATE Demo Site 6, our pilot site in Geneva with TPG. Then we have an induction charging station and the added value in transport with INTIS, a data capture systems and the hidden value of CAN knowledge with Teutonica, and leveraging data in Demo 6, achievements to date and future potential with THIRST. And after each session, we have also a short Q&A session. And if you would like to ask questions, feel free to do. Our speaker for today is Quentin Matthews. He's an engineer at TPG with 8 years of experience in Europe research on autonomous mobility, energy systems, and urban transport innovation. Our second speaker will be Dr. Ralf Effenberg, CEO of INTIS, and he is a leading expert in induction and wireless charging for electric vehicles. And our third speaker will be Stelios Kokas. He's a research assistant at THIRST and a PhD candidate in artificial intelligence and focus on advanced optimization and data-driven solution for electric bus fleets. And our last speaker will be Julius Banuskevicius, and he's a sales manager at Teutonica, specializing in fleet telematics solution for public transport and logistics, and he will share his hands-on experience for major European fleet projects. Now I will hand on to Quentin Matthewson. He will be the first speaker.
So hello everyone. This is a small presentation of the demonstration for Geneva, Demo 6 of the INFLATE project. So here on this map, you can see Geneva. Geneva is a very small area close to the French border that is international, not only for the UN or other things. There's a lot of companies here, and there's a lot of people living in France coming to Switzerland. So public transport is very important. And what we're trying to do in this demonstration is having a better, more fluid way to arrive to work for everyone. So I'll show later on a zoomed presentation of where we want to do this on-demand transport. We've been working on European project for some time now on autonomous vehicles, hydrogen vehicles, and for the INFLATE project with electricity. Something to keep in mind is that we only have one electricity provider because it's a state electricity provider. So this is what we're working with in Geneva. This is a legal obligation. Next slide, please. So what do we want to do with the on-demand transport? We want to not be in the center of Geneva. We want to be in the countryside. We want to provide something that is interesting for customers. We want them to not bring a car. We want everyone to be to have access to the center of the city. And for what we did in this area that you can see in blue and green is we provide on-demand transport today. This on-demand transport replaces 2 fixed lines and is way cheaper this way. And we have more customers daily. Today we're using different types of vehicles, some diesel engine vehicles. In the future, we'll have a vehicle that has hydrogen and electrical vehicle as well. What's interesting to note is that soon we will have autonomous vehicles going there. Those autonomous vehicles are electrical vehicles, and we want to have a 24/7 fleet operating. So what do we do in this demonstration number 6? We have this on demand. It's very interesting. It's new for us, and we're comparing this on demand with a fixed line we have today named TOSA. TOSA line is a line that charges all along the way. It's a fixed line, but we want to compare the use of this line with this on demand. We want to also have some comprehensive data capture, meaning that we're not going to only rely on the data we acquire from the booking, but also the data from the vehicles themselves. And we want a smart way to optimize our fleet and to have them also being completely autonomous with induction charging. So that's the information concerning the demo 6. Any questions? Yes, Lima?
Hello, hi. I just had a question in terms of the data protection. So, what is your approach for the passenger data protection, and how do you authenticate, validate, like in a sense, on-demand booking to prevent fraud or misuse?
That's a very interesting question, actually. In terms of GDPR, we have some rules internally at the state. So we have to be compliant with those rules. And those rules are the servers have to be in Europe. We have to do some audits on the software. And we also follow the accounts. So to use the on-demand transport, you have to create an account. This account can be used, it can be abused. So meaning that if we see that a client is booking and never showing up, we can blacklist that user. So this is how we can make sure that there's no abuse on the system. Is that sufficient for you? Yes, Lima? You're muted for now.
Oh, sorry, I was speaking. I'm so sorry. Thank you so much. Would it be okay if we have time if I ask one more question? It was a very interesting presentation, so I have a few questions. If you don't mind, I could ask one more.
Yes, please do.
Yeah. So I wanted to ask, since you mentioned about the electricity provider, so I just wanted to check, since I think you mentioned about one electricity provider, why do you only have one electricity provider? And is this viable long term in?
So this electricity provider is the city. So we have an entity named Industrial Services of Geneva, and they provide all the electricity. So what they do is that they generate their own electricity. They use this electricity and send it to us. But they are the ones choosing to buy and sell electricity from other places. So they are already doing this work of selecting electricity from different places. So they have backups if needed. So that's how it works for electricity in Geneva.
Okay,
Yes,
thank you so much.
I can compliment
Yes.
that. So in Switzerland, the liberation of the energy markets is not the same level as in the European Union. So there's still a little bit of monopoly of the biggest electricity companies. So at this moment here in Geneva, everything goes through the official one in the canton, that is SEG. But they are, of course, buying electricity from different sources, but they still have kind of control.
Thank you, Maher. Okay, next presentation. We can go. So next presentation is going to be Mr. Dr. Effenberger. So he's going to share his screen.
Yes, I will share my
Okay, I'm
screen.
gonna stop sharing my screen.
Mhm. Do you see my screen now?
Yes.
Just a presentation. Good morning to everyone, to all participants of today's ENFLATE meeting. My name is Ralf Effenberger. I'm CEO of INTIS GmbH, and I would like to talk today about wireless charging of EVs in public environment. Why is it so important to mention here in public environment? Public environment means non-discriminative access to wireless charging infrastructure by everyone here in Europe. So if one from Spain is coming to Germany, he should have the right, and it should work, that if he has equipped his car with wireless charging technology, that he can charge at any station in public environment, here also in Germany as an example. Okay, let's start. First, a few words about INTIS. INTIS is a company which has been founded in December 2011 in Hamburg. Just move this away. It's a 100% subsidiary company of IEB GmbH, which is a test service provider in Munich, space testing, aerospace testing, automotive testing. INTIS has about 15 years of experience in wireless charging. What is our heritage? INTIS has been, or the people which are working now for INTIS have been working in the past, before 2011, at the German national maglev test track Transrapid. And the last model of Transrapid, which was a TR09 meant to be used in Munich, was already equipped with 2x 250 kilowatt wireless charging, which was very impressive for us. And then after the operation of the test track has been closed, we decided to investigate whether wireless charging technology can be downscaled to sizes available under a vehicle to provide the right size of coils, much smaller than for Transrapid, and to provide to do wireless power transfer with high efficiency as well for electric cars. As we are in public environment, we have to fulfill certain standards or norms, and most of the norms for wireless charging are organized at level of IEC, ISO, or SIE. INTIS provides wireless power transfer solutions turnkey. So that means providing the infrastructure, which is roadside parts, which you can see, for example, in the photograph down on the right side, with a cabinet and with a coil on the road, as well as providing all equipment which needs to be installed into a vehicle. We maintain combined charging, so even if something is equipped with wireless power transfer technology, also DC conductive charging is possible via CCS or CHAdeMO or whatsoever. It's meant for use in public environment, and especially for applications in automotive sector, industrial, maritime applications, and micromobility. And INTIS provides a German representative at IEC. the standardization committee. So what's wireless charging? Just brief, we have not much time. Wireless charging is a technology where via a magnetic field, the energy is transferred. So you need at least two coils like in a transformer, but the difference to a transformer is that you have a quite large air gap between the two coils. Sorry. In order to work at that high air gaps, we need to change, or we need to go to a comparably high operating frequency, which is set in the standards and to be in the range between 79 and 90 kilohertz. So it's not 50 hertz like in our grid, but it's 79 to 90 kilohertz. So the primary coil, which is in the road, is exposed or gets an alternating current, electric current with a frequency in this range, 79 to 90 kilohertz. So we have the transmitter coil in the road, and we have a receiver coil in the vehicle. And of course, left and right of it, let's say, there's a lot of electronics which you need to accommodate this wireless charging. And the communication might be interesting also here in the group between the road and the vehicle is obviously wireless, has been decided to go to wireless LAN. It's covered by a norm, a standard at ISO, which is the 15118. And 15118 describes all parameters and messages which need to be communicated between the vehicle and the road infrastructure for charging, for safety, and so on. Which also means that in this protocol, there is a lot of data contained which are related to the charging situation, including battery voltage, of course, ID of the vehicle, is it allowed to be used, what is the state of health of the battery, and so on. So all this can be provided to the infrastructure via this wireless communication and is available for the user in order to see, is the battery stage okay, what is the health status, and so on. And there are several auxiliary functions also to be provided. Foreign object detection. So if there is something in the gap between the two coils, which is of metallic material, and this risk to get hot, then the system has to be switched off. This is supported by foreign object detection system. Then living object detection, if one puts his hand in between the gap between the two coils, then the system will have to be switched off. And there's also vehicle positioning assistance, which is needed to place the vehicle well above the ground side coil. What are the current performance data? Just briefly. First, the difference to cable charging is, of course, that we do not require any driver interaction except that he has to place the coil at the vehicle over the coil, which is which can be even done automatically, or to be done by the driver. If this is done, in fact, he cannot avoid having access of the vehicle to the grid. And one may decide what to charge, when to charge. The grid operator may say, okay, now at the moment there is a lack of energy in the grid, so let's not charge now, but let's charge in 1 hour later. That can all be decided by the grid operator. So there is no dependency. For example, a driver forgot to connect the car to the grid by cable, then you couldn't get access to it, but this can be avoided with wireless charging. Passenger vehicles and small vans are charged up to 20 kilowatt according to the standards. For trucks and buses, there are other standards where charging power is currently defined up to several hundred kilowatts. The air gap between the coils is set, in our cases, INTIS solutions, up to 30 centimeters. This is this is an adding up of the clearance of the vehicle underfloor to the underbody to the ground, plus some air gap which is related to the fact, which you can see here on the left side photograph, that the coil is integrated in the coil. There is a lid on top of the coil. This is necessary in order to ensure that the coil can be overridden by a 40-ton track. The power transfer efficiency is defined in the standard to be more than 85% at nominal power transfer. But all the stakeholders I know are achieving more than 90%. There is some questions always concerning magnetic field limits. Might be risky or not, this is at least a question. And product standards require here to confirm to so-called IGNIRP limits, which defines the maximum field strength, which is a risk to be exposed to people. And there are other discussions concerning disturbances of other radio services. Although we are operating only at 85 kilohertz, we have some harmonics, and we need to make sure that others, like AM radio services or radio amateurs, are not getting disturbed. And this is covered according to the CISPA 11 norm, where limits are defined for so-called Class A industrial and Class B residential environment. What kind of applications we distinguish in between? So we know static wireless charging. This is charging a vehicle while it's parking it's not moving. And more we see the discussion and the requirement also for bidirectional charging. That means we can transfer energy into the battery and we can transfer energy back from the battery to the grid. Then we also know dynamic wireless charging. This is charging while the vehicle is moving. Then you don't have a small coil, as you can see here on the photograph, but then you have a coil lane underneath the surface of the road. And whenever a vehicle is over that lane with these coils, then you can charge. INTIS has done already a project in 2000, I think finalized 2014, where it was shown that energy transfer of up to 60 kilowatts for buses and 30 kilowatt for passenger vehicles was possible. Preferred applications, wireless charging is one of the possibilities to charge electric vehicles, but we see a preferred application, especially for autonomous driving applications, where there's no driver, no one who can plug in something or plug out a cable for charging. For public transportation, why charging buses, for example, can be done at depots. That could also be done with cable. At end stations in service, where then the operator, the driver, wouldn't have to care about plugging in a cable or taking it out, or at any station where whenever you stop at the station, automatically charging of a little amount of energy is taking place. And here, when we see, if you see this photograph here, there you see an autonomous driving vehicle from Navia, and we could show that in the application in Bad Staffelstein, which was operated till the end of last year, the energy which was consumed by the vehicle on the 3-kilometer track with 2 of these coils at both end stations, it was confirmed that the battery status when arriving, or the energy consumed during one drive of 3 kilometers, with a max 10 minutes waiting time at the end station, the battery was fully recharged. So there is 24 hours, 7 days service possible without going to a depot or recharge the battery in a different way. And other services like fleet and transportation services, there's always a complaint of service providers, transport service providers, that people in the evening forget to plug in the cable, and then the disaster is big because next day the vehicle is not available for service because the battery is empty. And now with the wireless charging, only has to place the vehicle over on his dedicated parking spot, and then the charging is done automatically. Now let's come to the interoperability. Interoperability is very important as we are talking about public environment. And I just put down the norm landscapes, the standards landscape at IEC. IEC takes care about the roadside equipment for different technologies. For example, passenger cars, light commercial vehicles up to 22 kilowatts, which is covered by IEC norm 61980-1 to -3. Then there's other norms covered by IEC for charging power above or from 22 kilowatts for buses, trucks, heavy commercial vehicles, which is covered also by 61980-1 and 3, as well as by specific to this power class 61980-4. Then we are currently discussing a standard for micromobility applications, which is e-bikes, especially e-bikes and kick scooters, electric kick scooters, where we are talking about power between 100 watts and 3 kilowatts. And it's meant to set up a standard here where I'm asked to set up a draft and bring it to the discussion to specialists This is ongoing. And then there's another standard as IC, which is a 64980-6, which covers interoperability requirements for dynamic wireless charging. So why interoperability? To ensure non-discriminatory access to the wireless charging infrastructure throughout Europe. And what is taken into account while talking about interoperability? It's dedicated to there are these product norms which answer questions concerning requirements for subsystems, power paths, magnetics, and electronics. So you can imagine that the interface is a magnetic one, so you need well to describe the magnetic behavior of the coils and the electronics. The overall system is considered to be tested against interoperability requirements. Also the communication, which is according to ISO 15118, as well as the charging process. How is it charged? How fast, timeouts, and so on is all matter of interoperability. Then also the auxiliary functions like foreign object detection, living object detection, of course, safety aspects, and some others. Okay, let's see. I think we have not much time. What is currently ongoing at INTIS? One claims that the cost for wireless charging is still too expensive, is still too high. There is some truth on this. And what we are focusing currently is getting down the cost especially on the EV side. And the decision is made that the onboard charger, which is already part of the electric vehicle, usually, that this onboard charger is made fit for wireless power transfer, so we can use the hardware, and we have less hardware to be provided with the wireless power transfer equipment. So all the electronics, the power electronics in the car will be reused from the onboard charger. Then the other one is placement of all roadside components under the coil. You can see it on the photograph here. So all the electronics, the inverter, compensation equipment, whatsoever, we put into the road, aiming at that there is no cabinet at the place, which doesn't look nice, which is disturbing people, and so on and so on. So charging technology no longer affects the cityscape. This is what we are working on. Then we are progressing with bidirectional wireless charging. We talked about this, and we still have to enhance interoperability descriptions in the norms, which is done under the lead of INTIS, and this is ongoing. And now I have just a minute left, put some objectives which I found from ENFLATE project, especially the Geneva part. There were some questions to be answered concerning energy efficiency and battery longevity. And wireless charging is not a high power charging system. It's more an opportunity charging system, means charge as often as possible and avoid high power charging. High power charging is not good for the batteries, and that's why wireless charging is helping not to stress too much the battery. Lower operational cost. We don't need a driver for our application. We are avoiding high power charging, avoiding peak time costs, and so on. And then I have one answer for environmental benefits. It's invisible charging infrastructure. Vehicle to grid bidirectional charging is possible. The EV, so to say, also with wireless charging becomes part of an overall grid battery storage system. It's reliable and scalable. There is no connection to be made. There's no wear. There's nothing to be maintained. It's highly automated charging, and vehicle to grid implementation can be done without driver interaction. So that was my presentation. I would be very welcome answering your questions. Thanks a lot. Yeah, please, Lima.
Hi. Thank you so much for the presentation. It was very nice. I just have one question about could this system be pay as you use it, or what would be required for for the payment possibilities?
When you start charging, of course, you count the amount of energy which is provided to the charge to the battery, and there is one still open point because losses, energy losses, I hope this is going in the direction of your question. Energy losses are, of course, generated on the roadside as well as on the vehicle side. And both sides may influence the efficiency on the other side. It's simply like this for wireless charging. And especially in Germany, we have the so-called Eichrecht, and it has to be made sure that the user is only paying for the losses which are generated by his car part, so meaning the vehicle side. It's not yet fully concluded how to do that, but this is in progress. So making sure that the losses which are generated on the vehicle side to be paid or to be covered by the user, and the losses generated on the primary side, meaning on the roadside, to be covered by the operator. And moreover, whenever you place your car over such a coil, you will be registered, you will be checked whether you are allowed to charge, you are identified, you have your contract, and then automatic charging can be billed then directly to you. Was that your question?
Yes, thank you so much. Would it be okay? I think I had another question, but I think there's someone else, so I would just let it. Thank you. Thank you so much.
Welcome.
Yes, I have a quick question. I would like to know a bit more about demonstrators you have in the real world. I know you worked with the police. I know you worked with Navia. Can you tell us a bit more about those clients?
Let's look to this slide. This is a project which was completed in 2022, where 6 charging plates have been placed in the road along a line, which are meant to recharge taxis while they are waiting anyway for their passengers. So the idea was, if we have waiting times with taxis, which is unavoidable because next client is not there, you should use the time to charge. So the taxi jumped from one to the next charging plate, 6 in a row. And then we have learned that the waiting time they anyway have to cover. Using this for charging, here wireless charging, they can refill the batteries in the way that 24 hours daily support operation is possible. So this is one example, taxis in Cologne. Then one is here, as I talked about, is Bad Staffelstein, where we recharge 2 autonomous driving vehicles. We had another project, it was with the Netherlands, which was called Contactlos Laden, which was also with an autonomous driving shuttle. Then we have converted several passenger cars, different types. And currently we are working together with the police in Lower Saxonia to convert a vehicle I think it's a 97. So I think INTIS is a company, I would say worldwide, which has provided most of the demonstration projects or demonstrators in real life.
Thank
Awesome.
you so much for those examples.
Yeah, welcome. Other questions? Yeah, Lima?
Yeah, I had one other question about the charging capacity. So what is the fasting charging that we could have today on the road, for example, for a bus to go from 20% to 80%, how much time would it require?
This is depending, of course, on the energy you have to provide to the battery and depending on the consumption of the vehicle while the service is done. Let's just make an example or 2 examples. The autonomous buses here have only a 64 kilowatt hour battery, and the manufacturer of the battery didn't allow us to charge with more than 11 kilowatt. The wireless charging here installation is made for 22 kilowatt, but we were not allowed to go up to 22 kilowatt. If you have to from 30 to 80% to recharge your battery, then it's maybe 50 kilowatt. And if you would apply 11 kilowatts, it's about less than 5 hours to recharge fully the battery. But this is not what we are aiming at. We want to aim at the end stop to recharge exactly the amount of energy which has been consumed on the track. And let's take another example, which is buses, which we have done together with MAN. We came to the conclusion that wireless power transfer system of up to 150 kilowatt would be fully sufficient to recharge buses in a Munich example applications, even in winter with heating the bus and so on. So for buses, 150 kilowatt is realistic, and for autonomous driving, I would recommend to go up to 22 kilowatts. Charging technology allows more, but we should not overdo it. We should just put in, also for cost reason, what is necessary to recharge the energy consumed while the vehicle was in service between the two end stations, for example.
Okay, thank you so much.
Welcome. Okay, there are no further questions, so I would like to give back to the organizer the screen.
Thank you so much. I will share my screen then. Can you see it? Can you see the slide?
Yes, it's perfect.
Yes.
Okay, great.
Would it be possible for myself to control the slides?
I'm not sure, but you can tell me and then I can go to the next slide.
Understood. I'll just do big pauses. So,
Okay.
Hi, my name is Julius, and for the next 10 minutes, I will provide some knowledge about the new upcoming laws, CO2 emission regulations, and how Teltonika can help out with your projects. For those of you who haven't heard of Teltonika, we are a GPS manufacturer based in Lithuania, Vilnius, with more than 2,500 employees worldwide, if possible. However, Teltonika is a part of IT group, which consists of different departments, so networks regarding routers, telemedicine for smart gadgets for lone and elderly people, manufacturing facilities where we produce all of the hardware here in Vilnius, EV charging stations, and Teltonika Telematics, where we supply GPS trackers and are able to help out for the ENFLATE project. Since Teltonika already sold more than 22 million trackers worldwide, we have a portfolio of hardware ranging from 20 to 30 devices for specific use cases such as trucks, agriculture, generators, buses, public transport, insurance, construction site monitoring, and many, many more. Specifically for this project, we have chose one of the most advanced devices in our portfolio, and it's called FMC 650. This is a device that we categorize as the most professional due to it having the most functionality, as one device can cover more than 10 different use case ranges. Let's explore a bit more. The European Commission has introduced one of the most ambitious climate regulations in the transport sector. Since 2019, manufacturers have been required to cut the average emissions by 15% for both cars, vans, and heavy-duty trucks by this year, with an additional 15% reduction planned for 2030. These rules apply across the industry, meaning that eventually everyone will need to comply. The positive part is that with the ENFLATE project, we are already ahead of the curve and taking real steps to meet these targets. In this context, for those of you who haven't heard, in Switzerland this year there's an e-toll happening, which means an approximate 60,000 trucks will need to be equipped with GPS tracking device to monitor the vehicle and the trailer itself. The same hardware that we use for the ENFLATE project is going to be used for this e-toll as well, because of two special functionalities. FMS Eco Driving. Let me expand a bit. Many clients, investors, and partners increasingly require proof of environmental responsibility, including lowering the fleet emissions. Companies with greener fleets may win more contracts, especially where clients prioritize sustainability. To address this with our professional GPS tracker, we offer FMS Eco Driving feature, which helps to reduce fuel consumption and promote more efficient driving behaviors. By analyzing driving behavior, Eco Driving solution helps fleet reduce the fuel consumption by 10 to 15%. It means lower fuel bills, less environmental impact, and more money saved for the other operations. But the question is, how much money could we save? On average, a single heavy truck fuel consumption could be around 30,000 liters annually. By monitoring how fast the driver accelerates or how often they do harsh braking, we could prevent that. And imagine this across a larger fleet for 500 trucks. The savings can reach over 3 million euros per year. It's a clear indicator of how much financial impact an eco-friendly approach can have on larger operations. And these savings are not just about fuel. Optimizing fuel consumption also means reduced strain on your vehicle, leading to lower maintenance costs and longer vehicle lifespan. If we are able to save that much, the question arises, why don't we do it for electric vehicles as well? And well, we already do. This is an OBD device, FMC003. We use it for most common EV cars because it's already possible to do predictive maintenance by monitoring these EV parameters. The good news is that you don't need to know how to install the device as long as it's configured and plugged directly inside the OBD socket, where we are already able to monitor the vehicle. However, if a vehicle has been modified externally, just like in the ENFLATE project, we will need another device to capture this information. And that is where we come back to the same device, FMC650. I previously mentioned that there was two functionalities that are crucial for this project, and the second one is called manual CAN. With manual CAN, the type of the vehicle does not matter. Whether it has been modified or altered, as long as we know the specific parameters we are targeting, we can detect it and record it. When these parameters are recorded, the information is transmitted to your software, where you can view all of the vehicle data and perform calculations to identify specific events or conditions. In this slide, or in this scenario, knowing how the battery is aging in real time helps prevent degradation. So we can avoid harmful fast charges when the pack is hot, balance usage across vehicles, and flag cells that need attention before they actually become a problem. This also enables us to do predictive maintenance, spotting early warning signs, so the device is, the service is planned and not disruptive. In short, with the right EV parameters, fleets charge smarter, protect the battery, cut costs, and keep the vehicles on the road, which is the most important thing. We already discussed what data we can track from the electric vehicles. Then the next question is, how do we do it? A couple of years ago, to collect this type of information, we would have to connect the device to the wires directly. In most scenarios, it means cutting the wires open and losing the warranty of the vehicle. With today's technology, we have ECAN02, a wireless contactless reader. To capture CAN information, we only need two wires, CAN low, CAN high, as shown in the picture. When placed inside this casing and closed, the ECAN02 starts capturing this information, which will be sent out to the FMC650 and then to your software. This same data-driven approach sets the stage for the next regulatory milestone, which means from 1st July of 2026, Europe extends smart tachograph requirements to more vehicle classes in international operations, including light commercial vehicles that are over 2.5 tons. In short explanation, DDD files are the tachograph's work logs. They show when the driver has drove, rested, and worked. Today, many companies use USB kits to download these files from the tachograph, but we are human and people forget them or even lose them, and that can mean big fines for the companies. With this device, FMC 650, we can capture the DD files remotely, thus avoiding manual work and ensuring the proper data has been collected. And while preparations doesn't have to start today, using the FMC 650 in the ENFLATE project now means that the team is already working with the hardware, connectivity, and workflows needed for compliant tachograph data management, which will make your next year a lot easier. So how do we even get started? Well, first, if possible, please, you contact us with your use case and you tell us what do you want to track. I myself set up the configuration. You install the device, or we have partners that are able to help out. And then voila, enjoy receiving the information about your vehicle and live tracking. And that is done. From Teltonika side, we don't offer a software platform. We are a hardware manufacturer. However, we do also have partners that specialize in software telematics. Each software UI is unique, but all of them do the same task, providing fleet information. And I hope with this information, we are able to keep your fleet safe and efficient. Thank you. If you have any questions, don't hesitate to connect via email or LinkedIn. I'll be able to help out. Yes, Rolf.
Okay, my question. Thanks a lot for this very interesting presentation. It's very impressive. I have a question which is related to the positioning accuracy you can achieve with your satellite-based GPS or whatever it is in the future. Why I'm asking the question, because we need a positioning accuracy for wireless charging, which is plus minus 100 millimeter the transversal to driving direction and plus minus 75 millimeters in driving direction in order to keep high efficiency of wireless charging power transfer. So what do you think? Can we achieve today or maybe in the future, maybe with something which is coming up, by only using GPS information, can we achieve such positioning accuracy? Why? Just one remark. When we did the project within autonomous driving shuttle buses in Bad Staffelstein, we learned that we could achieve with the support, software support, which was provided by the vehicle, but only with the help of what is it called, this radar LiDAR system. So you have to put, for every station you have to calibrate. It would be nice to avoid this with a proper accuracy provided by the GPS signal. What do you think about this?
For this specific use case, it would be hard since millimeter accuracy is already difficult. From Teltonika side, we already have trackers that provide, let's say, 1 meter accuracy. And for almost any use cases, that is sufficient enough for most, let's say, clients. But in the future, I could get this information, and it would be my honor also to connect with you and provide this information later on.
Thank you very much. Lima is asking a question.
I think there's another question. Lima, I think you can ask your question.
Hi, thank you so much for the presentation. I just had a question while listening to your presentation. I heard that since you guys are the hardware providers, so you don't, but you have partners in terms of softwares. I was just wondering how does this data safety is being assured? Because since it is it's a very important data, and I believe it could be misused in so many ways. So how it is assured that this data is not misused and it is like it's used safely and it's transferred safely in a sense?
Well, one thing is that Teltonika GPS trackers, we do not send any information to ourselves, which means if you are going to be using a software platform from any client, the information would be directly sent to their software. And for example, in Switzerland, we also have software providers that have all of the database here in, let's say, Switzerland. And there are also other unique functionalities such as TLS certificate or MQTT protocols, which helps us avoid that the data would not be misused that is not intended to.
Thank you. I just have a follow-up question in that you say that the data will be not misused. How safe is the hardware itself in terms of the attack or any other security, the hardware itself in terms of security and privacy or attack surface, anything like that? How safe is the hardware itself?
I would say very safe, and there's a couple of reasons for it. The first one is that it does not matter what manufacturer you are. You have to stand by the law from the European Union, let's say for data privacy, which means each year there's new upgrades being made to the devices, so we keep it safe. And it's no secret, as Teltonika and previously I mentioned, that we have sold more than 22 million devices worldwide. So most of the clients trust us. And if there was any incident that would happen, then everybody would know. But until now, we are completely safe.
Thank you.
I see there's another question in the chats, but I know that Sert has to go forward for now.
Mm-hmm.
So we'll just have this question afterwards.
Understood. Thank you very much.
Stelios, it's your turn to rock.
Yes, hello. Hello from my side. My name is Stelios Kokas, and I'm part of Center for Research and Technology, HELAS. I'm also a PhD candidate. And my job here is to introduce you what we are doing in the ENFLATE project regarding Geneva and the transport. And our main challenge is about the optimization of energy consumption in the TPZ transport inside Geneva. We have a lot of things that we need to take into consideration in this project, and we can wrap it up in 5 different bullets, meaning that we need to ensure that we have the passenger pickup and drop-off time reassured according to what they need through the TPZ Flex application. We need to ensure that we will have the minimum possible energy consumption during the passenger tour inside the city and the specific areas. We need to also ensure that we will have the optimal shuttle indoor environmental conditions aligned with the previous objective of the minimum possible energy consumption. We also try to provide with the fleet orchestrators a digital twin of their fleet for simulation of adding new routes, new buses, how everything will be different or enhanced, etc. And finally, we need to provide solutions for the flexibility in charging. So if we could wrap it up into these 5 challenges that we're trying to do in Geneva. Next slide, please. So if we could translate these 5 challenges into actual services, we could end up with 3 different services. The 3 mobility services, as we call it in the project. The first one is called forecasting of in-vehicle environmental situational awareness. So that's how we're trying to consolidate the indoor environmental conditions and align them with the energy consumption output. Then this links to the second service, which is the automated energy consumption management for the autonomous shuttles, bus, trams, whatever we have in our fleet. And finally, since we have this input of the energy consumption, we can optimize the route with our challenges of the pickup and drop-off time and the passenger selections generally. Next slide, please. So, getting those services, we translate them into this conceptual flow. Okay, so we can see the 3 dots in there: the route optimization predictions, the sensor-based environmental conditions, and the actual passengers, providing data to the general service suite of tools. We use a lot of artificial intelligence in order for us to be able to produce outputs and then go back to the actuator layer, which is TPZ in this occasion, and make those plans and those predictions actual actions, if I can call it. So next slide, please. So in order for us to do it, we studied a lot about data collection, which is the hardest part in those kind of situations. First of all, we started by getting the information of the charging station placement strategy. Okay, we have this area, for example, to check that you can see here called Champagne area, and we needed to see whether we have the busyness of the stops, where we need to place the charging stations and help the place those charging stations. And also, one of the key factors that we took into consideration about this busyness, as we call it, is the proximity of key points of interest. For example, there are some rural areas, some industrial areas that a lot of people are working on. So that should be into consideration. Next slide, please. Also, we need to take info of the data about the electric vehicles that the people are using in the TPZ Flex. So we got the manufacturer manuals and specifications to do that. And that's how we started constructing our algorithms about their energy consumption, the maximum speeds, and also the rural regulations about how much each bus can run into the roads when they stop, etc. So we're starting a little bit by collecting data and simulating the real scenario. Next slide, please. Also, one of the main concepts we need to do, these vehicles need energy. Okay, how we can achieve that and also optimize the energy consumption and the energy charging. So we need to ensure that the electric vehicles will operate 24/7 and will not charge overnight. We need to adjust ourselves to the business objectives of the mid-shift charging, and that no passengers are on board during this mid-shift charging. No charging should be done during the peak hours to avoid service disruption. We should also ensure that the optimal charging rates should be between 20 and 80%. All 4 charging stations should be available for use. The closest free station is the one that will be selected from the EV to go and charge. And finally, the routes will have to be designed in order for the EV to maintain their battery level within the 20 and 80 optimal range. So all these considerations into our algorithms, into our services. Next slide. Additionally, we need to have a view of how the booking data are actually. So there are a lot of attributes, there are a lot of different information coming from TPZ on these bookings about the booking, the status, the passenger information, which was encrypted. So we didn't have any specific information on this aspect for the GDPR reasons, timestamps, pickup and drop off information, driver and vehicle information that will do this route. And this was on the on-demand booking data that the TPZ Flex services. So we had a lot of data to check on our validity. Next slide, please. Finally, since we have all this data, we need to place sensors. We need to place a lot of different sensors in order for us to collect all those data about the energy consumption. As you can see from the slide, we use 5 different sensors to do that. And we used also Teltonica, as was previously mentioned, which helped a lot. From these sensors, we collect energy consumption, state of charge, voltage and current, charging status, speed, outdoor temperature, vehicle live localization, acceleration, cabin temperature, humidity, and many other things. Okay, next slide, please. So, how we gather everything and make that a solution. AI will help us to solve this problem. The first thing is about getting all the routing algorithm, the constraints into the actual service. So what we said earlier, we need to guarantee that all passengers are picked up and on their selected pickup time and dropped off by a selected drop-off time. And many other things that we said earlier are already injected. Next slide, please. We adjusted our ways into heuristic modeling and insertion-based heuristic modeling to be specific, and our evaluation is based on the impact on the distance, time, and energy consumption, based also in the constraints that we said before. And the objective function that we added there is about minimizing the total travel distance and time extension across all routes. And for the static data that we have, that the people are already booking or beforehand of their route, everybody will be guaranteed that they will reach on their selected drop-off and pickup time their destination. And also we will have the dynamic data that someone picks right now, and we will see how this happens in our modeling. Next slide. So, as I mentioned, we have 2 different schedulings. The static one that I already pre-planned my route previous day, that tomorrow at this time I will leave from this point and I want to reach that point. Dynamic is that right now I'm requesting like a cabin, like a taxi for my route, and although I'm not prioritized regarding the static ones. So everything those should be ingested into our requests and make the best possible situation from all these requests. Next slide. So additionally, before all the routing, we added also the forecasting of the EV battery levels. We use a lot of different solutions with the AI, and we have already published our papers about it. But the main concept is that we could effectively forecast the battery of the EVs, and in order for us to plan more efficiently our routes according to the booking requests. Next slide, please. So we did this, we planned our routes, we did with the energy consumption and the indoor environmental conditions inside our shuttle, and we started testing scenarios. As you can see here, the static requests, all of them were scheduled. On the dynamic requests, more than half of them were scheduled. Also, you can see here on the right that also you can see that the energy consumption was reduced, and because on the static routing, as you can see, we have no charging events because we efficiently planned our routes. And on the dynamic routing, we reduced it a lot to 3 only charging events. You can see how our different buses from the fleet moved on the charging battery level, and they were going down, and around 7:30, something like that, they went most of them for charging, okay, which was in the mid shift. Next slide, please. And one of the main things that we need to do, okay, we design everything, okay, we do the AI services. We are not the drivers. We are not the ones that will actually do the route. So give the end user the chance to engage. So we build a dashboard or a platform that the driver can effectively see where he is, where he needs to go, which passenger needs to be picked. And also, they are getting energy minimization suggestions. You know, you're driving a little bit more fast. Probably you should go that way, because we are forecasting the way that the route will go. And also you can see on the pop-up already new requests that will lead you to new optimized route using digital twin algorithms that I will explain later on. Next slide, please. So there is another screenshot of how everything can be seen. You can see all your passengers, your car data, the forecast of your battery level for a period of time, and when it should be better for you to go and charge. So we give you all the information from the different models to the drivers for them to be able to facilitate with the actual route plan. Next slide, please. And here also we are trying to give also the information about the indoor environmental conditions of the vehicles, so you can actually make some changes like close the AC, do that, and probably that would be in a future level would be automated by done by us. Okay, done by the TPZ, done by the actual service actuators. Next slide, please. But we didn't stop there. Okay, our goal here was also to provide some services for the fleet orchestrator. The fleet orchestrator is organizing everything, but we need to see whether we can make some changes. And how to do that? By leveraging the technology of the digital twin. We tried to simulate the whole Champagne area inside a platform with all the services and the algorithms being ingested inside the objective functions. And that's how we done it. We took our objective, we used Sumo simulation technology. All the input were inside our model, and the output was the simulation of the whole fleet transport. Next slide, please. Here you can see the specific conceptual flow of how we did it with using the bus stops data and the Sumo. Here I have a video. I don't know if I have the time to show you the video, but if you ever want, you can find this presentation, please do that. You can see how the static and dynamic route can be simulated inside the digital twin, adding new stops, and how it changes all the passenger booking data and moving around. Next slide. That's all from my side. If you have any questions. Yes, Lima.
Yeah, thank you so much. I have two questions. One is about what are the difficulties that you face when you aggregate all of the data while aggregating the data initially? I also have one. Should I ask both questions together, or should I ask them?
Hit me. Fire away.
Sure. So the second question was, when you were presenting the dashboard, I just had a question about the accuracy of the prediction. How accurate is the dashboard prediction, and was it tested? If yes, how was the test? Like what was the accuracy level if we compare it with some similar other platforms?
Okay, so I will start with the first question. So regarding with the aggregation of the data, usually the hardest part is ensuring that the data from all these heterogeneous sources can be collected, clean, and synchronized in near real time. That was our hardest task. For example, the most common challenge that we had was about different formats and protocols, from CAN bus data, telematics APIs, station logs, etc. Data quality issues that we had, such as missing or noisy sensor readings, maybe some latency and scalability also was one of the things that we found hard to deal with. And finally, one of the main concepts, whenever we are collecting data and personalized data, it's about the cybersecurity and privacy constraints that we are dealing with all this operational and location data. So this was the main challenges about aggregating all those data. And on your second question about the accuracy of the algorithms, the first thing was that we did a lot of testing. Okay, we collected a lot beforehand the data before the the data, we collected open data sets in order for us to simulate our algorithms and provide the best solutions about the accuracy. And we tested with the real-time data of the TPZ, and actually it reduced a lot the energy consumption, the passenger waiting time, and the general orchestration of the fleet. So we are happy and confident with our solutions on this aspect. Of course, there will be further analyzed and further advanced, but right now they serve the scope in a very efficient way. Any other question?
Thank you, Stelios. Maria, I think you have the question.
Well, I had a question, but it was the same as the previous one and it is already answered, so I'm covered.
Thank you.
Perfect. Thank you, Stelios. Lima has another question.
Yes, please.
Sorry for bombarding you with so many questions.
It's okay.
I just had one more question about, it was actually really interesting, so hence so many questions. But my second, another question is about how hard would it be to use the tools developed with a new type of vehicle, like hydrogen, and having it its own charging station. So how hard it will be to adjust the tools developed for any other type of vehicles that are, for example, with hydrogen or something like that.
Okay, yes. Nice question. Usually the difficulty mainly depends on data compatibility rather than the vehicle technology itself. Our optimization tools are designed with a modular data ingestion layer so as long as the hydrogen, for example, vehicles and their refueling stations can expose key operational parameters such as energy consumption per kilometer, refueling time, etc., we can integrate them with minimal re-engineering. The main effort would be to define the new data schemas like hydrogen flow rates, tank pressures, or whatever data, and to calibrate the optimization models to reflect hydrogen different refueling dynamics and cost structures. So in short, it's not a complete redevelopment, but it does require data standardization, API integration with charging infrastructure, and retraining of the predictive models to capture the specific energy and cost behavior of hydrogen fleets.
Are there any other questions? If not, then thank you so much, Stelios.
Thank you.
And thank you everyone for joining us today. And I also would like to thank you to our speakers with these really interesting presentations. And I think then we can stop the webinar, and I wish all of you a nice day. And yeah, thank you for joining.